A hollow cylinder of inner radius 0.18 meters spins around a vertical axis, okay, with a constant angular speed of 8 radians per second. Okay. A bug sits on the inside surface of the cylinder and does not move relative to the cylinder. The normal force of the cylinder on the bug is 0.035 newtons. Okay. Take this in. Got it. So what is the mass of the bug? Okay, so let's see here. So we know we're given a normal force here. And that normal force is, so if we look at this from the top, so we look at it from the top view, we have a bug right here, and this is spinning. But the bug is spinning, the bug is stationary with respect to the spinning cylinder. So there's an centripetal acceleration, centrifugal going outward, and so there's a normal force pulling it inward. So we have a force normal, which is going to be mass times acceleration, which will be mass times v squared over r. So this, just to kind of show what I did here, this is the centripetal acceleration. Whenever you spin, you're maintaining the same speed, but your velocity is changing because velocity is both magnitude and direction. And when just the direction is changing without the speed changing, that's going to have some sort of acceleration because your velocity is changing. Because the velocity is, again, both the magnitude and direction. The way you quantify that is through centripetal acceleration, which is v squared over r. And that's what this bug is experiencing. So the bug is being pushed out on the inside of the cylinder, and the normal force is the force that's pushing back, making him not move inward or outward, radially, so to speak. So we know that normal force is always mass times acceleration. In this case, acceleration is v squared over r, and so we know this value. We don't know that value, that's a question mark. We're given that value, but it's in radians per second. We're going to have to convert that. We want meters per second. And we're given the radius, the interior radius of the cylinder. So first thing we're going to do is we're going to convert 8 radians per second into, I'm going to put radians in parentheses there because radians isn't actually a dimension. So it's just there to show you that it shows you what it's measuring, but it's not like radius isn't dimension like meters or kilograms or second. It's dimensionless. So I like to put it in parentheses. Either way is fine. So to convert radians, so in a circle, it's going in a circle, we would have 2 pi, I gotta do radians, per one circumference. And one circumference would be 2 pi r radius. So there's 2 things you can always do in math. You can always add 0, and you can always multiply by 1. So this part right here is multiplying by 1 because this is a circumference of a circle. So a radian can both be an angle, a measurement of an angle, but it also can be a distance, a radius, so to speak. So when you talk about the circumference of a circle, you could call it either 2 pi angles, radians for angles, or you can call it 2 pi distance in basically radiuses going around the circle. So conceptually, this is the circumference of a circle. Also, this is 2 pi r, which is circumference of a circle, where r is measured in meters. Okay, so 2 pi's will cancel out, the radians will cancel out, even though they're kind of never really even there. And we have 8 times, the radius is what, 0.18? 0.18 meters, 0.18, and then it'll be meters. We still have the seconds, and now we got the units in meters per second as we wanted earlier. So converting this over to something reasonable on clear, 8 times 0.18, click, 1.44. 1.44 meters per second. So we can switch this around, mass of bug. I'm going to get rid of this equal sign over here. Blue? No, we already did blue. Light blue. Okay. So looking at this equation, we'll move velocity squared down here, move radius up there, and we have 0.035, which is the force normal. Is it? It is. Times radius, which is 0.18, 0.18, all divided by velocity squared, which we have over here, which is 1.44 squared. The velocity is 1.4. We square it because that's part of the equation. Okay, go back to our calculator. So I have 0.035 times 0.18 divided by quantity 1.44 squared. I don't know if I have to do the quantity, but I just don't want to take my chances. Okay, boom, 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 boom. I'm not quite sure how the order of operations works with a TI-83 calculator. Okay, so move it over 3.038 grams. And I just converted it to grams instead of writing 10 to the negative third. Kilograms. Okay, so let's see what we want. 3.038. And that looks like this one right here. So if we move that over and then call this 3.8, it's about the same. Okay, so the mass of the bug will be 0.00304 kilograms, or as we said, 3.038 grams. And we were able to find that based on the normal force that's provided. Okay. Now it's going to ask us, what is the minimum coefficient of static friction that is required in order for friction alone to be the only force preventing the bug from falling? For this one, I'm going to look at it from a side view, maybe a side view. So a view kind of like this. So here is the side of the cylinder, and then it wraps around kind of like this. Whoop. And then the bug will be probably gray. I assume most bugs are gray, right there. And there is going to be a force normal, like so. And there's going to be some sort of force gravity. And then opposing this force gravity will be force of friction. I'll write it like this. Force, friction, static. Because it's not moving. Preventing the bug from falling. Okay. So, I don't even know if they had forces of coefficient of frictions above 1. Interesting. Usually you see it around like 0.3, 0.4. Okay. So, let's see here. So if we do a balance of forces here, we can see that force gravity and force due to friction have to cancel each other out. So force due to, that's a terrible F. Force due to gravity equals mass bug times gravity, which will equal force normal times static coefficient of friction, which will be, yep. And then normally we would also write this as mass times gravity, because usually the force normal is due to something like just sitting on the ground, or mg cosine theta if we have something on a plane. But this case, we're just given the force normal, and that force normal is due to a spinning cylinder. Probably a lampshade or some such. Looks like a lampshade. So let's see here. We know gravity, we know mass of the bug, and we know force normal, so we can find this coefficient of friction. So we have 0.035, which is the, nope. See, that's why I'm getting ahead of myself. So mass will do 3.04, 3.038, and I'll do times 10 to the negative third. That's mass times gravity, which is 9.81, divided by 0.035 newtons, because I basically just moved the force over here. That should work. Let's see if that works. So we got that still up there, which is convenient, times 9.81 divided by 0.035. And we get 0.8516, 0.8516 6. Looking at this answer, we can come over here, and that's probably going to be E. So instead of 2, if we had 1/6, it would round up to 0.852. So we're good there. So that'll be E as the minimum coefficient of static friction, which makes sense at minimum because it could be bigger too. We said the minimum because we assume that that's just where it breaks and the bug would start falling. The coefficient of friction could be bigger, causing it to definitely stay, even if the lampshade slowed down a little bit. Which of the following correctly describes the net force acting on the bug? Okay, so this is a good question. Draw a picture real quick. Here is the rotating cylinder. And we have our bug here. So we have time t equals 0, bug over here. We'll say time t equals 1, bug is here. So it's moving, it's stationary relative to the lampshade does not mean that it is stationary. So this will be the velocity at point 0. We'll call this velocity at point 1. And so the net force, so the velocity changes. So change in velocity equals something, which means that there is acceleration, which implies that there exists an acceleration. Acceleration is something too. Because to change the velocity, you're going to have an acceleration. Acceleration changes velocity. And so we have an acceleration. So sum of all forces, if something is not moving, will be, okay, sum of all forces equals mass times acceleration. If you have no motion, then you have sum of all forces, or if you have no change in velocity, then sum of all forces equals 0. This implies delta velocity equals 0. So we know this is not the case, so we have the first one here, which says the net force is 0. There has to be a force. The velocity is changing because even though the speed is constant, the direction is changing. And so this is not true. The net force has at least some component in the tangential direction. Okay, so if there was a component in the tangential direction, then the bug would basically be moving faster than the lampshade. You can think of it as the bug basically crawling around the lampshade as the lampshade is also spinning. But we're told that he's stationary with respect to the spinning cylinder. Therefore, there's not going to be any net force tangential. And by tangential, it means it touches in one point. So something like this. These things that I drew right here, that's those velocities are tangential to the spinning cylinder. But since these are going to all be the same length, same magnitude, this part will not be true. The net force points purely towards the center of the cylinder. Now this is the centripetal acceleration right here. So yes, the acceleration is going to be purely towards the center of the cylinder, and that's what will give you the change in direction of your velocity vector. So for this one, the answer will be C. There is a force, and this force only points towards the center of the cylinder. So this is actually a pretty good set of questions here. It talks about some of the concepts involved with rotational motion and acceleration. So really like this one. Hope that helped. I will see you next time.